Hi, I am Fei Xiaong. I am presenting our work, Learning Extremely High-Density Crowds as Active Matters. Video-based high-density crowd analysis and prediction is a novel and challenging problem in computer vision. A key challenge is the scarcity of high-quality data. Cameras are often placed far from the crowd, resulting in noisy and low-resolution data. Even with state-of-the-art crowd counting and localization methods, accurately capturing individual motions remains difficult. Moreover, as the crowd density exceeds 5 people per square meter, crowd dynamics can become violently chaotic. To address the challenges, we propose a novel learnable active matter model. This model features a specially designed stress-strain relation that reflects empirical crowd behavior, integrates autonomous behaviors and self-propulsion through the toner-2 equation, and is formulated as a neural stochastic differential equation system, allowing for both physical realism and data-driven learning. Here are the key contributions of our work. We propose a novel video-based framework for analyzing and predicting extremely high-density crowds, incorporating a new differentiable physics model. We develop a crowd-specific material model that treats crowds as active matter and further design a hybrid Eulerian-Lagrangian scheme, crowd MPM. Finally, we demonstrate its advantages in capturing complex crowd dynamics compared to existing methods. This figure illustrates the end-to-end framework of our method. Starting with optical flow estimation from crowd videos, we generate the corresponding velocity field and sample initial particle positions. These particles are then evolved using our proposed crowd MPM. Finally, we compute a loss by comparing the predicted motions with the observed ones. For a single time step, the input sequentially passes through two modules, ParaNet and the MPM layer. ParaNet, implemented using a continuous convolution network, estimates key force-related parameters directly from data, eliminating extensive hyperparameter tuning typically required in physics-based models. In MPM layer, we design a special stress-strain relation to reflect the empirical observations in high-density crowds, fundamentally differing from conventional materials like water. Additionally, we represent crowds as active matters by integrating the toner-2 equation. Here we show experimental results. We first introduce 4 datasets: drills, Hodge, Hellfest, and Marathon, covering diverse scenarios, crowd dynamics and densities. Since there is no similar existing methods, we adapt several closest methods as baselines, including physics model, physics-informed neural network, deep learning methods for scene parsing, sequence prediction and video prediction. Similarly, as there is no established evaluation protocol, we employ mean square error on optical flow and velocity fields as metrics. We first conduct a quantitatively evaluation on short-term prediction. Specifically, we use duration of 8.2 second for drill 1 to 3, 2 second, 1.6 second and 2.4 second for Hodge, Hellfest and Marathon respectively. Our results are the average and the best result based on 10 trials. The top 3 results are highlighted in red, orange and yellow. Overall, our method achieved the highest performance across both metrics on all datasets except Hodge, where our method is slightly worse than CVP. In drill 1 and Marathon, we obtain the best mean square error on velocity field and the second best mean square error on optical flow. For further generalization tests, we conduct cross-behavior prediction by training the model on drill 1 and testing the model on drill 2 and drill 3. Obviously, as behavior shifts from peaceful, drill 1, to neutral, drill 2, and then to aggressive, drill 3, model performance declines consistently across both metrics. Our method can also serve as a simulator for crowd analysis, which is not feasible with purely data-driven baselines. This figure presents simulation examples where color represents stress magnitude. Compared to the original evacuation scenario, top, both a wider exit, middle, and an added obstacle, bottom, help reduce the stress. Finally, we conduct noise robustness experiments on the drill 2 dataset. To assess temporal robustness, we randomly mask 0%, 50%, and 70% of video frames to simulate temporal discontinuities. For spatial robustness, we introduce various types of noise with varying shapes and magnitudes, for example Gaussian, uniform, and their mixtures. The results demonstrate that our model consistently maintains reliable performance, confirming its robustness to both temporal and spatial noise. In summary, we introduced a novel neural stochastic differential equation system to represent extreme high-density crowds as active matter. To the best of our knowledge, our method is the first to learn physical models for extremely high-density crowds. We also demonstrated our model's superiorities on multiple datasets. Thanks for watching. The paper and code are available on our website.